Hello, my name is Christian Lay. I am a PhD student in environmental engineering at Purdue University, and today I'll be talking to you about a paper evaluating the impacts of municipal water to rainwater source transitions on microbial and chemical water quality dynamics at the tap. Harvested rainwater is increasingly being used to offset municipal water use. However, recent studies have shown that when you transition between different water sources with differing water chemistry, this can cause the pipe scale and biofilm to be released from the pipe walls and into the drinking water. Rainwater and municipal water have very different water chemistries. For example, rainwater has a lower pH, it is often UV disinfected, and it has a lower mineral content. Whereas municipal water has a neutral pH closer to 7, it is often chlorinated, and in this case, since we were using a groundwater source, it has a higher mineral content. In this study, we tracked changes in the calcium and magnesium, total trihalomethane formation. In addition, we monitored the changes in opportunistic pathogens and also the changes in metals. So the objective of this study was to determine if transitioning between these two different water sources can cause the water quality at the tap to be degraded. In order to gain a better understanding of what happens to water quality at the tap after a transition between rainwater and municipal water, we developed a following set of objectives. The first objective was to evaluate the changes in metal concentrations following the transition between rainwater and municipal water. The second objective was to identify changes in microbial growth and opportunistic pathogen proliferation. And the third and final objective of this study was to identify possible relationships between changing the influent water chemistry, for example, changes in ions, pH, and alkalinity, and how those factors affect drinking water quality at the tap. The field testing location was a residential building that had PEX pipes, as well as water-efficient fixtures, and a total of 9 fixtures were sampled during the study. Some of those fixtures included untreated rainwater, municipal service line water, as well as a water heater, a kitchen sink, a bathroom sink, and a shower. In order to test these objectives, the home was running on municipal water for an entire year from October 2017 to October 2018. During that time, over 50 sampling events occurred. After that, the water source was transitioned to rainwater, and 10 sampling events occurred between January 2019 and February 2019. Then the water was transitioned back to municipal water from February 2019 to March 2019, and a total of 10 sampling events occurred during that time. This is a chart showing the changes in aluminum, copper, iron, and zinc following the transition between rainwater and municipal water. Aluminum concentrations peaked in hot water fixtures during the rainwater phase and gradually decreased as rainwater was replaced by the municipal water. This effect may be due to the decreased pH of the rainwater corroding and interacting with the anode rod in the water heater. Copper concentrations in the drinking water were positively correlated with alkalinity and negatively correlated with pH. Copper corrosion may thus be attributed to changes in water alkalinity. Previous solubility models for copper release have indicated that copper release rates increase with increases in alkalinity and decrease with an increase in pH. This is a comparison of the Legionella species and Mycobacterium species gene copy numbers, as well as the total cell counts after transitioning between the rainwater and the municipal water. So the decreasing rate of Legionella species in the water heater over time as the municipal water began to replace the rainwater may be due to the intermittent variation in incoming gene copy numbers, or a variation in incoming chlorine concentrations, or even due to inactivation by the increasing copper concentrations found during the municipal water phase in hot water. During the rainwater phase, concentrations of Legionella species remained constant after treatment into cold water fixtures, but they decreased slightly for the hot water fixtures and water heater. Of all the fixtures sampled during the rainwater period, Legionella concentrations were highest in the shower. This is likely due to longer stagnation times and the distal location in the building plumbing network. What are the lessons learned from the study? First of all, there may be some trade-offs between rainwater and municipal water quality. For the rainwater studied, none of the parameters exceeded the U.S. EPA health and aesthetic-based drinking water limits. However, with the municipal water, some of the individual DBPs exceeded the EPA-suggested MCLG of 0 micrograms per liter. So why does all of this matter? Rainwater has a lower pH and low alkalinity, and it may have caused a release in iron, zinc, and aluminum scale from the water heater and the building's plumbing. This study really highlights the need to examine rainwater not only from the tank, but also within the building plumbing, because the rainwater can interact with the pipe, biofilm, and scale to cause a release in contaminants. If you have any questions about this study or any of our related studies, feel free to contact Andrew Welton. His email is listed below, as well as his website, plumbingsafety.org.